Welcome to Unit 1 of Calculus and Vectors exam review. Unit 1 was limits. We introduced the concept of limits, which grew into derivatives. So it was a pretty fundamental foundation for what we did. We're going to look at a couple of the main processes that we do to work with limits. We're going to start with evaluating indeterminate limits. If you remember, we had 4 strategies, and we're going to see a little bit of each one of the 4. And this is only when a limit is indeterminate would you use one of these strategies. Now, just a quick review on what a limit actually is. Give you a couple of examples. If you remember, we used these pictures and we talked about different important positions of these pictures to really highlight what is the purpose of a limit and what is true of a limit. So for this one, this function doesn't exist at this point, whatever it is, but the limit does exist at this point. And that might be useful, as we saw with slopes of tangents and derivatives and everything we did in calculus. It's pretty useful to be able to use this concept that the function may not exist, but the limit does. Okay, so that was one example. And then another example might be something like this, where this is kind of the opposite. The function does exist at this point, but the limit doesn't, because the left-hand limit doesn't equal the right-hand limit. So generally speaking, that's kind of what we did with limits. What we understood about limits, and as we were exploring them and what they are. But anyway, to get to actually solving indeterminate limits, if you remember, let's take a look at one. If you remember, the key to these, to start these, is doing a quick substitution. So 0 is obvious, the bottom is obviously 0, because if I sub 0 in for x, I get 0 on the bottom. What about the top? 0 minus 64 is negative 64. Cube root of that is negative 4 plus 4 is 0. So this is indeterminate, and the 3 that we look at will be, but it's always a good idea to do that quick check. If you try to use one of these strategies on a limit that isn't indeterminate, it won't work, and you won't know why, and you'll get very confused, and it's very frustrating. Okay, the 4 strategies we have are factor. We'll see a little bit of that, but that's just, polynomial factoring probably is what you're doing there. Using a conjugate to rationalize was another one of them. Substitution, and then if you have fractions over fractions, you're doing some kind of common denominator work or something like that. So those are the 4 strategies that we saw. In order to evaluate this limit, because of the cube root, I know that it's a substitution, swap out, change a variable, goes by a few different names. And to start this question, we have to do the change of variable first. So we are going to substitute for this problematic part of the expression of this limit, which is the part that has the cube root. So you're just going to pick whatever variable you want. If you remember, we often use a and u for some reason. So I'm going to choose to use a, and I let a equal this problematic part, just like that. Okay. This is a mini 3-step process we do off to the side before we can continue with the limit. So that's the first step. The next step is always solve for the other variable. So I'm going to cube both sides, because that will get rid of that cube root, right? 1/3 all cubed, going to be gone. And then I don't really need these brackets anymore, and then I'm going to add 64 to both sides. So that's sort of step number 2. And step number 3, people forget to do this, and they do one of 2 things. They either leave x here, but if I'm subbing these x's out, I can't have an x here as well. So I have to change that as well. So they might just leave x alone. If they don't, they might just say a approaches 0 and just change that to an a. But in this case, that would be wrong. Once in a while it works out like that, but not in this case. So in this case, how you do it, we got to figure out what's happening. So how you do it is you say as x goes to 0, and then you take x and you sub it in here to figure out what a is. So off to the side I'll show this, but normally I would just do this in my head. So this is the cube root of negative 64, which is negative 4. So as x goes to 0, that tells us a goes to negative 4. And now I can rewrite this limit statement like that. So see how now everything is in terms of a, and I've changed this problematic part to a. So a plus 4, And then the x, I now have an expression for that as well, and it's a cubed plus 64. And everything is in terms of a's, and I've fixed that, and I've fixed both parts of this. Make sure you write the equal sign in the right spot. It does not go between these two parts of the limit. These go together. Now, this is a little factoring one. It's a good one to review because it's a sum of cubes, and we have to remember how to do that. And so I take the cube root of each part, and the sign stays the same. Square the first part, multiply these two together and change the sign, and square the second part, and it's always positive. And if you do this right, first of all, it was indeterminate here, it should still be indeterminate there. That's a tip that you're on the right track. If I sub -4 in here, it better still be indeterminate. Doing this swap out stuff is not going to change it from being indeterminate. So this is still going to be indeterminate at this stage and at this stage, because I haven't changed anything yet. But now this factor of a plus 4 is what is causing it to be indeterminate, because the -4 subbing into these two causes the 0 over 0. So when I divide those out, this is where we have done the work to fix this and solve this limit. Got to write this out one more time though, and then we can sub in. And that's 16 plus 16 plus 16, which is 48. Okay, so there's your change of variable substitution strategy for solving indeterminate limits. See what's next. We got one of each of the other types. So we'll do this one first, which is pretty obvious that it's fractions. So there's a couple ways you can do it. You can just get a common denominator on top, and in a couple of steps, no matter how you start, it'll look the same. The other way you can do it is multiply this top and this bottom by the same thing. So that's what I'm going to do. And I multiply by the product of the denominators of the top, just the top part. So 3 times x plus 3 over 3 times x plus 3. Okay. And so that means on the bottom, I'm going to do that first, I get 3 times x plus 3 times x minus 3. Okay, so all of those multiplied together. Now when I do 4x over x plus 3 times this, the x plus 3's are gone, and it's just 4x times 3, so I get 12x. And when I do the 2x over 3 times this, the 3's are gone, and I get minus 2x times x plus 3. Now you could expand that at the same time if you want. So I've got negative 2x squared and 12x minus 6x. Okay, factor on top. Again, the -3 is causing the x plus 3 to be, oh, it's not -3. How did I change that? Careful now. So the 3 it means the x minus 3 is the problematic part. So this has to be x minus 3. Sometimes that's a tip that you can force it, but in a common factoring case like this, it kind of just has to work. So I can factor out a negative 2x, and I end up with x minus 3. And again, that is a clear indication that you are doing this correctly. It would be quite a fluke if it worked out anyway. Okay, gone and gone, and that's what was making it indeterminate. Write this out one more time. And then we can substitute and solve. So those are gone, and negative 2 over 6 is negative 1 over 3. Okay, so there's your fractions and fractions strategy. And the last one of these that we are going to do is using a conjugate to rationalize. Sometimes you have to do both the top and bottom, and it's a lot longer. In this case, we only have to do one. That's good. And what do I multiply by? Well, I multiply by the radicals that you have, but you change the sign that's between them. And you multiply on the top and bottom, so you're multiplying by 1. And you want to know what happens when you use this conjugate. You don't want to be expanding this. What a waste of time. We've set this up so that it just gets rid of, when I do the square root of 4 minus 4x times itself, it's like squaring itself, and I just end up with 4 minus 4x. So you need to know that. Be careful. This one has to be in brackets because you're subtracting. Okay, again, I don't want to expand the top. That would be a waste because the x plus 3 is what I want to be dividing out. And I get negative 4x minus x, which is negative 5x, and 4 minus 19, which is negative 15. And I got to write this out one more time at least, maybe two. And I believe if I factor out a negative 5, I get the x plus 3 that I want. Okay, they are gone. Square root of 4 minus 4x. A lot of people miss this top part. It just disappears. I don't know if they get lazy in how they're writing it, or they just forget it somewhere, but it can often disappear. So this ends up being the square root of 4 minus 4 times negative 3, so that's 4 plus 12, which is 16. Square root of that's 4. And negative 3 plus 19 is again 16. Square root of that is 4. So this is 4 plus 4 over negative 5, which is negative 8 over 5. Okay, and those are all the types. We saw a little bit of the factoring type. Those are how you can solve indeterminate limits. Okay, the other kind of question we're going to do here. Use the definition of a, that's a mistake, of a derivative. To determine a general expression for the slope of the tangent, so we can't sub in at the beginning, so it's a little bit more work, then use that expression to determine the slope when x is 5. So if you remember, this is the formula where a derivative equals the limit. This is the h formula that we learned. Now there's also the x minus a formula, but when it says definition of a derivative, it means to use this one. If it just said find a general expression, you could use either. And this is f at x plus h minus f at x over h. Okay, so I'm subbing in x plus h into this function, and then this is just the regular function and doing all of that over h and doing it as a limit, and then using whatever strategy we need. So this is 5, okay, for this indeterminate limit, because it will be indeterminate. You don't have to check these ones. All of that over h. So this is the same as the example B that we just did, where I am doing x plus h plus 5 common denominator, or I'm multiplying. I should do it like this. I should show this a little bit better. So x plus h plus 5 times x plus 5 over itself and multiplying them to clear the denominators on top. So this one, the x plus h plus 5 cancels with that, and I get 5 times x plus h times x plus 5 minus 5x, and the x plus 5's cancel now, times x plus h plus 5. We're going to expand the top, but we are not going to expand the bottom. So expanding the top is x times x, which is x squared times 5. If you make a small mistake here, you'll probably catch it because the next step won't work. X times 5 is 5x times 5 is 25x. H times x hx times 5, so 5hx, and 5 times h times 5 is 25h, minus 5x squared, 5xh, or 5hx, minus 25x. And when we look at what is happening on top, take a look at everything that cancels here. 5x squared is gone. The 25x is gone, and this is what has to happen. And the 5h is gone. 5hx is gone. And every term that's left has to have an h in it. If you are left with any constants or any simple x terms like this or like this, then you have done something wrong, substituted wrong somewhere or expanded wrong somewhere. Because the top, in this case, doesn't actually, we don't need to factor it, but otherwise we would common factor out the h so that it can divide with this h. And it is no longer indeterminate. And we were supposed to be coming up with an expression, so we sub in h equals 0, and I get x plus 5, or x plus 0 plus 5 times x plus 5, which is 25 over x plus 5 squared. And that's our derivative. So there's our expression. The second part of this was to determine the derivative at 5. So that's 5 plus 5 squared, which is 100. 25 over 100 is 1 over 4. Okay, so that's a big one too, definition of a derivative. Setting it up properly is obviously key, using the right strategy, and then expanding properly and expecting this step to happen where the h's divide to 1. Okay, and that is Unit 1 of Calculus Exam Review.